This is the presentation for our machine learning project, which is a weather condition predictor for rocket launches. All right, so the purpose for us to create this project is to create a model that can predict future weather conditions and then use these predictions to determine whether a specific day is optimal or not for a launch.
First, we gathered historical weather data using the Meteosat Python package. We selected Kennedy Space Center weather records from 2010 through 2019, giving us a full 10 years of daily data. The variables collected were temperature, relative humidity, precipitation, wind speed, pressure, and cloud cover. These were chosen because they were all weather factors that can influence rocket launch safety. Next, the data was divided into training and testing sets. 80% of the data from 2010 through 2019 was used for training the model so it could learn patterns between weather conditions and launch outcomes. The remaining 20% from 2018 through 2019 was reserved for testing to evaluate how accurately the trained model could predict go or no-go launch decisions on unseen data. We then analyzed the quality of the training data by graphing the major variables. Temperature showed a clear seasonal trend, which is useful for machine learning because patterns are easier to recognize. Wind speed, humidity, and pressure had more variation, but still provided realistic environmental behavior that can affect launch conditions. Overall, these four variables were consistent and valuable for model training. Some variables had poor quality data and were removed before training. The precipitation data contained mostly missing or zero values, with one unrealistic spike. Cloud cover also showed an abrupt shift after 2013, indicating inconsistent measurements. Because of the reliability issues, both precipitation and cloud cover were excluded, and the final model used temperature, humidity, wind speed, and pressure.
For our machine learning implementation, we decided to use a feed-forward Keras model in which we have two inputs, 4 hidden layers with TANH activation functions, and one output. We used 20, 50, 50, and 20 for the nodes with the idea that it would fit well without being overgeneralized. For the testing data, we went ahead and plotted it on a plot with the day of the year and the respective conditions, with the red line being our model output. Temperature, because of its seasonality, worked out really well, while the other 3 conditions had some issues, which repeatedly gave us results that were unusable.
Harmonics were then implemented to help provide the neural network with a better representation of time. It helps the model understand complex seasonal patterns, so the neural network doesn't need to learn the patterns from scratch. There are 3 different sine and cosine groups in the harmonic. The first captures the yearly trend, the second captures the fall spring asymmetry, and the third captures small fluctuations in the data. The day is divided by 365.25 to account for leap years. This has all the data points correspond to the same day across different years, allowing for the model to learn an average seasonal pattern that repeats across the data. It does not change or alter the data set, but rather give the model a harmonic representation of time. The team still used Keras and a feed-forward model, however adjusted from the first iteration to avoid overkill. The model consists of an input layer, 2 hidden layers, and an output layer. The input layer changed to 6 due to the 6 inputs from the harmonic feature. The hidden layers have a size of 16 neurons, so the model has enough to learn the harmonic inputs, but isn't too large to avoid overfitting. The hidden layers were activated using TANH, and finally, the output layer has a size of 1 neuron since we are predicting 1 value. Here show the results on implementing the harmonics. The iterations of the neural network shows the predicted values, which are in red, better fit the data.
Now that we had the data predicted by the model, we could use this to determine whether a day was good or not for launch. To create a score calculation system, weights were created for each category of meteorological data, those being temperature, wind speed, humidity, and pressure. Higher weights were given to temperature and wind speed, since those have a clearer influence on rocket launch favorability based on the Falcon 9 rocket launch criteria by NASA. Humidity and pressure have a more vague relationship with launch favorability, so lower weights were given to those. And the gradient of score detractions given due to humidity and pressure changes are associated with lowering the air density, which would decrease air resistance during a launch. Finally, a threshold value of 70 was chosen as the total score needed in order to determine whether a launch was good or not.
As an alternative machine learning implementation, the team decided to take the 4 models that we previously had and combine them into a singular model with multiple outputs. To achieve this, we had to first adjust the actual data passed through it for the training to be able to properly use in the model. And to do that, we had to use the column stack to have the proper layout. We also had to change our actual model itself to still include the 6 inputs, which has the harmonic conversions on it, but we will have 4 outputs instead for each of the conditions. We also had to change how we pulled the data out. Whereas before we were able to use the model predict and be able to unstandardize the data all in a line, whereas now it had to be pulled first before we can undo the standardization. Overall, the singular model still worked, though there are some changes in the actual output. The model is a little less generalized than it was previously, and this was found out over multiple runs. So overall, the numbers of the nodes and things might need to be changed further if a singular model is kept.
While the models work well given the data provided, the actual limitations of the data itself influence how well it would actually work for our intended purposes of determining launch favorability. Specifically, Meteostat only provides daily high temperatures for a 10-year range, which we would need to properly get an idea of weather trends over an entire year. The lack of precipitation and thunderstorm information also limited how well we could determine launch favorability, as those could have a grand influence on whether a rocket should launch that day or not. Special thanks to Dr. Hubicki and our TAs Nick Gearman and Jacob Hackett for their help on this project.